Here is something nobody tells you before your first system design interview: you do not need to study 100 different systems. About 10 questions cover the overwhelming majority of what you will actually be asked. Something like 90% of system design interviews are a variation on the same shortlist. And here is the better news: one framework answers every single one of them. In the next few minutes I am going to give you that framework, 7 steps a strong senior candidate walks through out loud, and then apply it to the 10 classic questions, back to back. For each one you will get the same 3 things: the key requirement that defines the problem, the core design idea that solves it, and the main scaling gotcha the interviewer is really probing for. Learn the framework once, and these 10 stop being 10 separate problems to memorize. They become one process you run 10 times. Before any specific question, internalize the framework, because interviewers grade your process far more than your final diagram. 7 steps. Step 1, requirements. Split them into 3 buckets. Functional, what the system does. Non-functional, how it behaves, things like availability, latency, and consistency. And scale, roughly how many users and how much data. Never skip this. Jumping straight to a solution is the fastest way to fail this round. Step 2, estimates. Back of the envelope numbers, reads and writes per second, storage over a few years, bandwidth. You are not being precise. You are finding where the pressure is, so you know which part of the design has to be strong. Step 3, the API define the handful of endpoints, or the contract between client and server. Keep it small, resisting overbuilding is a signal of seniority. Step 4, the data model. What are the entities, and, more importantly, what is the access pattern? The way data is read and written is what drives your choice of storage, not the other way around. Step 5, the high-level design. Draw the boxes: client, load balancer, services, cache, database, and trace one request all the way through them. Step 6, the deep dive. Every question has one genuinely hard part, the bottleneck. Spend most of your time there, because that is what the question is secretly about. Step 7, trade-offs. There is rarely one right answer. Name the tension: consistency versus availability, cost versus latency, simplicity versus scale, and justify the call you make. That is the spine. Requirements, estimates, API, data model, high-level design, deep dive, trade-offs. Now watch it answer all 10. Question 1, the classic opener: design a URL shortener, something like bit.ly or tinyurl. The key requirement: it is overwhelmingly read-heavy. People click short links far more than they create them. A common assumption is around 100 reads for every write. That single ratio drives the entire design. The core idea: generate a short code, store a simple mapping from that code to the long URL in a key-value store, and put a cache in front so the hot redirects never touch the database. Encode the code in base 62, the 10 digits plus lowercase and uppercase letters, and just 7 characters give you around 3.5 trillion possibilities. Plenty of room. The scaling gotcha the interviewer is really fishing for: how do you generate those unique IDs at scale, without collisions? Hashing the URL risks 2 different links colliding on the same code, which you then have to detect and retry forever. The cleaner answers are a counter encoded in base 62, which is unique by construction, or a dedicated key generation service that pre-makes a pool of unique keys offline and hands them out on demand. Nail unique ID generation, and you have nailed this question. Question 2, design Pastebin: store a blob of text and serve it back at a short URL. It looks like the shortener, but the twist is the payload. The key requirement: you are storing and serving text blobs that can be large, not just a tiny short to long mapping. The core idea: separate the blob from its metadata. Put the actual paste content in object storage, something like Amazon S3, and keep only the metadata in your database: the paste ID, the owner, the expiry, and a pointer to where the blob lives. Then serve popular pastes through a CDN so you are not refetching the same content over and over. The gotcha, and the mistake juniors make: do not stuff large blobs into your relational database. Databases are poor at serving big payloads at scale, it bloats your rows, and it wrecks your caching. The other half of this question is expiry. Pastes usually have a time to live, so you need a background cleanup job or a TTL to purge them. Blob in object storage, metadata in the database. Say that clearly and you sound like you have built this before. Question 3. Design a rate limiter, allow at most n requests per user per time window, and reject the rest. The key requirement: enforce a limit, say 100 requests per minute, accurately, and do it fast enough to sit in front of every single API call. The core idea: use a token bucket or a sliding window counter, held in an in-memory store like Redis, keyed by user ID or IP address. A token bucket refills at a steady rate and each request spends 1 token. When the bucket is empty, you reject. A sliding window counts requests over the trailing time window. Both are standard, and both are cheap enough to run on the hot path. The gotcha: you are almost certainly running many servers behind a load balancer, so the count has to be shared and updated atomically. If 2 servers read the counter, both C99, and both allow a request, you have leaked over your limit. The fix is to do the counting inside Redis using its atomic operations, an atomic increment, or a small Lua script that checks and updates in one step, so the limit holds across the whole fleet. Distributed, atomic counting is the real problem hiding inside this friendly-sounding question. Question 4. Design a news feed, Twitter, Instagram, Facebook. Show a user the recent posts from everyone they follow. The key requirement: assemble, per user, a timeline of recent posts from the accounts they follow, and load it fast when they open the app. The core idea is the fan-out decision, and this is what the whole question turns on. Fan-out on write, also called push: the moment someone posts, you copy that post reference into the pre-computed feed of every one of their followers, so reading a feed later is just a cheap lookup. Or fan-out on read, called pull: you store each post once, and assemble every feed on the fly at query time. Push makes reads fast but writes expensive, pull makes writes cheap but reads expensive. The gotcha, and this is the famous one, is the celebrity problem. If an account has 50 million followers, fanning out every post to 50 million feeds on write is brutal, and most of those feeds may never even be read. So real systems go hybrid: fan out on write for normal accounts, but for celebrities and other high follower accounts, fan out on read, pull their posts in at feed load time and merge them with the pushed ones. Naming that hybrid is exactly what the interviewer is waiting to hear. Question 5. Design a chat system: WhatsApp, Messenger, Slack. Real-time one-to-one and group messaging. The key requirement: deliver messages in near real-time, both directions, plus presence, who is online right now, and searchable message history. The core idea: each client holds a persistent connection to the server, typically a WebSocket, so the server can push a message down the instant it arrives, instead of the client constantly polling for new ones. Route messages between users through a message queue, and persist every message to a database, both for history and for anyone who is offline when it is sent. The gotcha the interviewer probes: delivery guarantees. How do you make sure a message arrives exactly once, in the right order, even when the recipient is offline or on a flaky mobile network? You need per conversation ordering, acknowledgements and retries so nothing is silently lost, and a store and forward step so an offline user receives their backlog the moment they reconnect. Saying real-time is easy. Reliable, ordered, offline tolerant delivery is the part that actually earns the round. 2 questions here, because they share a shape: a queue feeding a pool of workers. Question 6. Design a web crawler, fetch and index a huge chunk of the web. The key requirement is to continuously fetch pages, extract the links on them, and keep going, at enormous scale. The core idea is a URL frontier, a giant queue of URLs waiting to be visited, feeding a pool of fetcher workers. Each worker downloads a page, parses out the new links, and pushes them back into the frontier. You track every URL you have already seen so you do not crawl the same page twice, and you stay polite, obey each site's robots.txt, and cap your request rate per domain so you do not hammer anyone. The gotcha is deduplication at scale, checking have I seen this against billions of URLs need something space efficient, like a Bloom filter, plus avoiding crawler traps, pages that generate infinite links to keep you looping forever. Question 7. Design a notification system, send push, email, and SMS reliably. The key requirement is to fan a single logical notification out across multiple channels, dependably. The core idea: accept notifications onto a queue, then have per channel workers, one for push, one for email, one for SMS, pull from that queue and call the right external provider, using templates for the content and honoring each user's preferences and opt-outs. The gotcha is reliability. Providers fail, so you need retries with backoff, but retries mean you might send the same thing twice, so you need an idempotency key to dedupe, and you need rate limiting and priority levels, so a flood of low-priority marketing mail never delays a critical security alert. 2 more that both come down to one clever data structure. Question 8. Design a nearby, or proximity, service, Yelp, Uber, find things near me. The key requirement is, given a latitude and longitude, quickly return the objects within some radius. The core idea is that you cannot scan every location on Earth, so you index space itself with a geospatial index. A geohash encodes a lat-long pair into a short string, so points that are near each other share a common prefix. Or a quad tree recursively divides the map into 4 cells, again and again, until each cell holds a manageable number of points. Either way, you bucket locations into cells and only ever search the handful of cells near the query. The gotcha is hot cells. A dense city center overloads a single bucket, so you subdivide busy areas more finely, and moving objects, like drivers, whose location changes every few seconds and has to be constantly reindexed. Question 9. Design typeahead, or autocomplete, suggest completions as the user types. The key requirement is to return ranked suggestions for a prefix within a few milliseconds, on every keystroke. The core idea is a tree, a prefix tree, built from popular queries, where each node can cache the top completions that live beneath it, so you do not rewalk the whole subtree on every letter. Back it with aggressive caching of results for the most common prefixes. The gotcha is ranking and freshness. You rank suggestions by popularity, and you have to keep the tree updated from live query traffic without rebuilding it on every request, usually by aggregating query counts offline and swapping in a freshly built tree on a schedule. Question 10. Design a distributed key-value store, or a distributed cache. This is the building block sitting underneath half of the other answers, so it is a favorite. The key requirement: fast reads and writes on simple key-value data, at a scale far bigger than any single machine can hold. The core idea has 2 halves. First, shard the keys across many nodes using consistent hashing, a scheme where adding or removing a node only moves a small slice of the keys, instead of reshuffling everything and invalidating your whole cache. Second, replicate each key onto several nodes, so the data survives a machine dying and reads can be served from more than one place. The gotcha, and be honest about this one rather than hand-waving, replication forces the consistency versus availability trade-off. This is CAP. When the network partitions, and at scale it eventually will, you cannot have both perfect consistency and full availability. You have to choose. A cache like Redis, or a store like DynamoDB or Cassandra, typically leans toward availability with eventual consistency. A system that must never serve stale data gives up some availability to stay strongly consistent. State which side you are choosing, and why it fits the requirements. Interviewers respect an honest trade-off far more than a claim that you get everything at once. So there is the whole toolkit: 1 framework, 10 questions. The framework, again: requirements, estimates, API, data model, high-level design, deep dive on the bottleneck, then trade-offs. And the 10, 1 line each. URL shortener, base 62 codes, cache the reads, generate IDs without collisions. Pastebin, blob and object storage, metadata in the database. Rate limiter, a counter in Redis with atomic operations. News feed, fan out on write versus read, go hybrid for celebrities. Chat, persistent WebSockets, and guaranteed, ordered, offline tolerant delivery. Web crawler, a URL frontier, dedup with a Bloom filter, and politeness. Notifications, a queue, per channel workers, retries and idempotency. Nearby, a geospatial index, geohash or quad tree. Typeahead, a tree of popular prefixes plus caching. And the distributed key value store, consistent hashing, replication, and an honest CAP trade-off. Notice how the same primitives keep coming back, caching, sharding, queues, and a deliberate trade-off. Learn those 4 moves, run the 7-step framework, and you can reason your way through a system design question you have never even seen before. That is roughly 90% of system design interviews in one sitting. The secret was never memorizing 10 answers, it is running one framework, and knowing, for each classic problem, the key requirement, the core idea, and the gotcha the interviewer is really after. I put a full written system design interview guide at the link below, and if you want structured practice across all of these questions, the system design interview prep pack is in the description, $24, completely optional. Subscribe for more system design and developer interview breakdowns, and I will see you in the next one.